Welcome to Section 6.7, Real-World Triangle Problems. At the end of this section, we should be able to answer these questions. When is it appropriate to use the law of cosines to solve a triangle? When is it appropriate to use the law of sines to solve a triangle? When is it appropriate to use the area formula to calculate the area of a triangle? When is it appropriate to use Heron's formula to calculate the area of a triangle? What formulas do we use to convert a vector to horizontal and vertical components given its length and direction? And how do we find a vector's length and direction given its horizontal and vertical components? Well, this section is a set of word problems that will place us in various situations where we will have to be solving triangles. So let's look at the different situations and which formulas would be appropriate for each of those situations. First of all, we should know the formulas. Before I uncover each of these formulas, you should quiz yourself and ask yourself if you know each of these laws or formulas. So the law of cosines. A squared equals b squared plus c squared minus 2bc cosine A. So you'll see that there are four different unknowns, a, b, c, and angle A. To solve for any one of those, we need to know the other three. So there are three sides and one angle. To work with this formula, we'd need two sides and an angle, or three sides. So the SSS gives us those three sides. So yes, we could use the law of cosines. Here we have two sides and an angle, which also allows us to work with the formula. Two sides and an angle, again, lets us work with the formula. Two angles and a side. Now I need at least two sides, so I can't use the law of cosines in an AAS situation or an ASA situation. The law of sines is our law of proportions, where sine A over A equals sine B over side B equals sine C over side C. Now to work here, again, we would pair up two of these proportions, which would give us two sides and their opposite angles. So I would need, with these four unknowns, at least one pair of a side and its opposite angle. With three sides, I have no angles, so I couldn't use the law of sines. With SAS, I would have two sides and their included angle, which means that I still don't have any pairs of a side and its opposite angle. So I could not use the law of sines to initially attempt to solve a triangle. SSA gives us a side and its opposite angle, so we could use the law of sines here. AAS, here we have two angles and the side opposite one of the angles, so yes. Now ASA, here we have two angles, this angle here and this angle here, and the side in between them. So at first glance, we don't have an opportunity to create a ratio with an angle and its opposite side. But since we have two of the angles, we can very quickly solve for the third angle, because all three angles have to add up to 180. And then we do have the ratio of a side and its opposite angle, so we could use the law of sines after that initial calculation. Now the area formula we learned in this chapter, the area is going to equal 1/2 side 1 times sine 2 times the sine of the included angle. So I need two sides and the included angle, the SAS situation. SSS doesn't give us enough information to immediately apply the area formula. Neither does SSA or AAS or ASA. Heron's formula is a way of calculating the area using all three sides and there's the semi-perimeter. where S stands for the semi-perimeter, the sum of the three sides divided by 2. And our formula is S times the quantity S minus A times the quantity S minus B times the quantity S minus C, the square root of all of that. This formula is specifically designed to work solely with the sides of the triangle, so the SSS situation. All these other situations, which involve angles, won't work until we've solved for the three sides, so our initial attempts would be fruitless. Now let's look at our vector information and concepts. Here we're given a vector with a magnitude and direction, or we're given a vector with horizontal and vertical components, using I and j as the unit vectors in the horizontal and vertical directions respectively. If we're given the horizontal and the vertical here, the blue vectors, and we're trying to determine the information about this red vector, well, we can see we have a right triangle, so the magnitude is going to be the hypotenuse of this right triangle, where we calculate it by taking the square root of the horizontal squared plus the vertical squared. Our direction angle, theta, is going to depend on whether it's an acute angle or an obtuse, and we'd have to look to see by examining our horizontal and vertical components. If the horizontal component is positive, then our direction angle would simply be the inverse tangent of the vertical over the horizontal. If, however, our horizontal component is negative, we need to apply the arctangent concept and add 180 degrees to our inverse tangent of vertical over adjacent. Now, if we need to go in the other direction, where we're given the length and direction angle, then we simply need to use the right triangle concepts, SOHCAHTOA, to solve for the adjacent and the opposite of our angle. So, in doing so, we find out that the vector can be broken down into horizontal and vertical components by taking the length times the cosine of theta for the horizontal component, and the length times the sine of theta for the vertical component. So let's recap. To answer these first 4 questions, when is it appropriate to use each of the formulas to solve a triangle or solve for the area, we need to examine the information we've been provided and then decide according to which information is needed for each of the formulas, as is summarized in this nice little table right here. Okay? To answer these questions of what formulas we use to convert a vector to horizontal and vertical components given its length and direction, well, we use these formulas down here. The vertical component would be L times the sine of theta, and the horizontal component would be L times the cosine of theta. If we're given the horizontal and vertical components, then we approach the problem as a right triangle problem, and we find the hypotenuse according to the Pythagorean theorem, and we find the angle using the inverse tangent or the arctangent formulas. If the angle is going to be obtuse, which we would know because our horizontal component is negative, then we would add 180 degrees to the inverse tangent of the vertical over the horizontal.